All right, welcome everyone, and thank you so much for joining us today. I imagine we'll have a few more people joining us as we get started, but not to delay today's proceedings. We're just going to run through a few introductory slides before I hand over to our presenters this morning. We're very grateful to have Artur Zolich joining us from Poland, and Andrea Faltynkova joining us based in Norway at the moment, but working together on the portable Catamaran drones. So we're very excited to be hearing about that today. Artur, you're welcome to bring up the slides when you're ready.
Okay, so I guess I'll get us started. Thanks so much for the invitation. Really nice to be here this morning. And yeah, today we're going to be talking about a project that myself and Artur have been working on for a couple of years now, that we call the portable Catamaran drones. We've also nicknamed these little drones Pamela for perhaps obvious reasons, perhaps not. If you're not familiar with the old TV series Baywatch, then this is a bit of an homage to a character there. But yeah, so I'll just kind of tell you a little bit of the background and the story of how this all got started. I myself am a chemist by training, and I work specifically in environmental science, and my focus is mostly on analytical chemistry. And I got interested in plastics in the ocean when I was on a cruise in the Mediterranean doing some research, and I saw just how much plastic there was. And so I kind of started getting into this topic of microplastics and learning about how we analyze microplastics and where we find them and how we can kind of figure out how much there is. And I realized that it's actually quite a challenge to figure out how much plastic there is, where it is, and that sort of thing. So this topic really piqued my interest, and then I started a PhD in 2019, where my focus was on improving analytical techniques for microplastics analysis, specifically in the marine environment. So that was my interest, and then from there, I kind of realized, okay, well, if I want to analyze microplastics, I'm going to have to collect microplastics from the ocean, and to do that, typically, we're using nets. Pretty simple technology. We've kind of adapted this technology from other marine sciences, studying usually phytoplankton or zooplankton. And it's a super simple setup. You just take a net and you drag it behind a boat, and then you see what you catch. So pretty basic. One of the challenges with this setup is that if you want to take multiple samples, then you need multiple nets and you need multiple boats. So it doesn't scale up very well. You have to take one sample at a time. You also, need a boat, which costs a lot of money. You need personnel to drive the boat. So there's a lot of logistics behind it as well. And I was talking about this with Artur. We just had a meeting, and I was explaining to him this process of how we take samples. And he essentially asked, well, why do you do it like that? That seems really time and resource intensive. Why don't you just make a drone that can carry the net and go out and collect the sample for you? And I'd never even thought of this as a problem, but with his engineer perspective, he could immediately see a better solution. So that is what kind of led us to the development of what we now call Pamela, or the portable catamaran drone. And here is a picture of how that looks out on the water. So here I'll turn things over to Artur, and he can explain a little bit more about the process for developing those.
Yes, so thank you. So my name is Artur Zolich. I'm a researcher at NTNU. And throughout my work at the university, I was working on bringing robotic systems, sensors, and embedded systems technology to the real-world applications. So I did my PhD in communication and control architectures of different types of unmanned systems. When we think about the drones right now, we usually think about the flying vehicles, but we expanded a bit, and we introduced also underwater vehicles, surface vehicles, autonomous buoys, satellites. We try to create a system of systems where we take the state-of-the-art technologies to solve a certain real-world problem. And over the years, we were looking in my team topics like fish tracking or providing environmental monitoring from measurements under the ice cover of the North Pole, or using the flying robots to provide communication for search and rescue situations. As Andrea mentioned, when we've been introduced to each other, we decide, okay, what we can do together, how we can combine our skills to address new challenges that researchers around the world experience in their everyday work. And that's how we looked at the problem of sampling using a plankton net. And quite a natural solution for me was, well, if we have the plankton net, if we need to use a ship or a boat in order to collect a sample, let's scale it up using the autonomous robots, autonomous vehicles moving on the surface of the water. And what are the benefits of such approach? Well, first of all, as Andrea already mentioned, we don't need to use a boat to support us in our operations. We don't have to physically be on the sea. We don't need some motorized vehicle to tow the net. Then if the robot is autonomous, if it can follow a certain plan, then we don't need to have a constant supervision over it. We can just release it and come back after half an hour on an hour and just pick it up off the water from a known location. So in the same time, we introduce the scalability. We can deploy several vehicles at once that will do their mission, and we just collect them after a while. Then we can make a system of systems. So we can think of new scenarios for the future. For example, where small vehicles are easy to deploy by other type of vehicles that have a slightly different capabilities like endurance or range. So we can drop small surface drones from a flying vehicle or from a big vessel and then collect them together. So it enables a lot of scenarios without increasing the involvement of personnel. Also, if we have a portable robot, we can sample areas where we cannot use a boat. There are some lake reservoirs where we are limited by accessibility to release other type of vehicles, or where we cannot disturb the nature with, for example, the bigger boats. One of examples here may be mountain lakes in Pyrenees, where, for example, accessing with a heavy boat is a problem. Then, if we remove a boat that tows a net, we also remove the effect of the ship hull on the water. So the layer of the water we sample is not disturbed. This was another enabler another thing we could enable using our small robot. And as I mentioned, the multiple robots can survey larger area at once. So when we have a fleet of 2, 3, 5, 10 vehicles, they can do they can scale up our work. We can collect 10 samples at once, or we can collect one sample just some meters behind the first one, making a replicate. So it triggers a new scenarios in which we can improve the outcomes of the research of scientists using the plankton net. And this was the very first visualization after our first discussion with Andrea. When we're thinking, okay, what we are going to look into, we thought, okay, this is our concept art of what are we aiming to. We have a bunch of robots. They sample certain areas. They are being carried by other type of vehicles. So this was the long-term vision. And then we started working on the topic. So we started very simple by just verifying whether this idea makes sense at all. So out of our first discussion, we made a super rough super simple proof of concept. We actually use the plumbing pipes, as you see on this photo, just to have the vehicle running as quickly as possible. And then Andrea was leading her master students on a field course in Norway in Sledvik, where for a period of around 1 week, they were using a vehicle, collecting samples in different areas of the place where the course took place, and provided us feedback, or okay, what to improve, what to make better, what will be a nice feature, which features has limited value for the final user. And a very important part of this process, why we actually did this process, is if you introduce something new to the user, something that hasn't been done before because of the traditional methods. In the beginning, we really don't know what should we focus on, what the user will need in the end. We need to make a rough prototype to get some experience, to get some knowledge about, okay, yeah, we need this and that. So out of this test, we get very valuable information, what we should keep, like, a simple design, and, and do this by clever component selection. But then we should introduce features like battery replacement systems, and some sample management solution. And the vehicle should stay cost efficient, portable. And one of the other things was that we would like to have an inlet that we can open or close. So we sample a certain area, not starting the moment we put the robot in the water, but later at some point. And through this discussions, through this feedback and further iterations, we were continuing designing of building the new prototypes of our solution. So this was an interactive process in which we ended up with 3 prototypes looking as presented on the photo, where we then actually named them, as Andrea mentioned in the beginning, Pamela, due to the reference to the Old Days TV series. And when you look at the design, we focus on usability and features which are relevant for the scientists and users. So the key one was the inlet. So the inlet of the robot is in front of it. So then we have undisturbed layer of the water that we sample, and you can use it in 2 ways. It can be rotated vertically or horizontally, because for microplastics we kind of want to sample the wider top layer of the water. But for other applications, like for example salmon lice detection, a vertical profile, a vertical volume is slightly more important. And then we also make the inlet actuated, as you see on the animation in the corner. So you can deploy the robot with the inlet out of the water, move to a location when you would like to start your sampling, then lower it to the position where the inlet is submerged in the water, and start navigating the path you want to sample. And then when you're done, the inlet goes up, and the robot comes back with a sample not affected, for example, by this by the distance between place we want to start collection of the sample and our location, for example, on the coast. When we look at the elements of the robots, we try to keep it as simple as possible. Less elements it means less things to fail. And I already discussed the inlet. It can be equipped with a flow meter if we want, but also you can get the information about the volume of water that run through the net based on the autopilot records of GPS track and its speed. Then we have thrusters. We have 2 thrusters on each side of the of pontoons, and then there are electronics. Is basically 2 boxes. One is a box which is completely sealed and there is no user intervention needed, while the second box contains the battery and satellite tracking system. So you are able to replace the battery very quickly without any tools, and also, like for example, in the rain, and not, let's say, laboratory conditions. A certain feature we enable in this robot is that we use commercial off-the-shelf batteries that are very easily accessible globally from basically power drills of one of the manufacturers. So you are able to carry this robot with you wherever you fly. You can take the batteries on board with you to the plane. They follow the regulations by the airlines of the airlines. And the rest of the robot can be packed in the check-in luggage. So with this construction, you are actually able to travel easily. You don't have to ship the robot before planned operations, which sometimes is an issue in our region, where, for example, someone would like to do deployments in Svalbard area or somewhere where it's or places where are inaccessible without going there by a plane. And then, of course, when you solve one problem, you create a new problem. So right now, the plankton nets and the cod ends, which are in the end of it, where the sample is stored, they're not easy to remove because, well, if you take 1, 2, 3 samples a day, this few minutes you will spend on removing the cod end from the net, from the touching it doesn't really matter. In our case, turnaround time when the robot comes from a sampling to deploy it again is 3 minutes. So quick replacement of a code end was an important feature in our case. So we developed this custom-made stainless steel code ends, which has a mesh size which is the same as the mesh size of the net we are using, where the sample is collected. And then, as you see on this video here, you just release a ring which connects the cod end to the net. And then we store the entire sample in a glass jar. It's also like quite easily accessible type of a jar. And then we can secure it with some silicone seal. Then we put a new cod end to the net. We replace the battery, and as I mentioned, in 3 minutes the robot is ready to go for a new mission. The battery on the robot lasts up to 1 hour. We are aiming at 30 minutes sampling plus a backup to come back for some other type of maneuvers where when we try to reach the shore. Sometimes the robot is affected by the wave, so we need a bit more maneuverability. So this was the use case scenario we are aiming at. Portability was very important. As you see here, this is one of our master students, Catherine. She had to bring the robots on the cliffs in some places where it was hard to reach. You need to usually carry the robot from even a car to a site where you deploy. So portability was important. Then you can also dismantle the vehicle into 3 main components and pack it into the box for shipment. So those are important feature. And as you also see on the photo on the left, Catherine is carrying 2 boxes. One box contains batteries for basically whole day of operation, and then also the glass jars to which the filters are being stored into. As for the deployment, you can deploy the robots from a pier or from a beach, from a cliff sometimes, and you just throw it in the water. We also were deploying it successfully from the motorboat. And in the beginning, we usually do a few maneuvers in the manual mode, where we just navigate using a joystick or on the screen of the tablet, and then set up the automatic mission, and the robot starts navigating using the autopilot and the GPS position system, which is on board. And the system proved to be so simple that at some point researchers started like giving it to their kids and to play with it, to navigate it, and the feedback I've heard is that we're quite good in that. So the gaming industry is also giving a positive contribution to the future scientists in terms of navigation of the robots. And then, of course, we aim at the users, researchers, whose focus is in biology, in chemistry. So we don't want them to be forced to have an extensive training, to have an extensive knowledge build up on electronics or navigation or robot control. We wanted to keep it super simple. So on the left, you see the tablet and the user interface that you use to plan the mission, to navigate the robot. You can control the vehicle manually or plan a path it will follow. But of course, sometimes there are requests, or there can be situations where we need some form of support by the expert user. So a robot is equipped with LTE communication. So it can be controlled both by the local user with the tablet shown on the photo, but also through the LTE, basically wherever we are in the world, if there is a mobile phone coverage. So we can access the expert features of the vehicles remotely, trigger, control the vehicle remotely. So we can envision a scenario where the only action user on site does is put the robot in the water and pick it out from the water when the mission is complete, without even having the tablet with them. And if things go really bad, fortunately, it never happened before, but we have a backup system where the robot carries a satellite tracker, which let us know every 5 to 10 minutes what is the current position of the robot. It's completely independent from the rest of the robot. If there is a battery damage, if something like this would ever happen, we will have independent localization where we can retrieve the vehicle. And as mentioned in the one of the first slides, the core benefit is the scalability of this solution. So in this photos here and screenshots, you can see two robots doing a sampling of the same location. They are being deployed. They were deployed 5 minutes after each other to make like 25 minutes runs to collect samples of the same area to get some better picture of the situation in the current region at a certain time. And we are also very often asked about the vehicle behavior on the higher waves. Maybe it's not very visible on the video, but we were experiencing 1.6 meter waves. And robot behave quite very well in this conditions. Its performance wasn't affected. It was more challenging for a user to actually take it out of the water, being washed by the waves hitting the coast. So we have a big trust in the robot and prove its performance also in not like a flat conditions. And so far, we're looking at introduction of the robot to a bigger community. Andrea has a great network in the microplastics domain. We are also in touch with scientists in the zooplankton and plankton research domains, where the plankton net sampling is also used. So far we had contact with several countries, around 8 countries. In the last several months, robot completed a number of missions in Norway, also in Ghana and Tanzania. We are at the same time discussing possible tests in new locations, in the new scenarios, which also include scenarios even like a research part of tourist cruises in the Arctic. And we've presented the vehicle on several gatherings, several other conferences in Europe, North America, and Asia. We also have a paper published on the vehicle. The data of the paper will be presented on the last slide in case you would like to follow. Yeah, and now we have this robot, so we are able to scale up the sampling. So let's now switch back to Andrea, so she can explain us what does it mean for the microplastics analysis. So thank you, Andrea.
Thank you. Yeah, so as Artur showed, we now have this really neat solution for researchers who are interested in trying to take samples quickly, get a large number of samples in a short amount of time, and also get replicates, which is something that, as per now, is really difficult, or I at least have never seen it done with a regular magnetrol, is to have a real kind of side-by-side replicate, which is something that's really important, obviously, when we're trying to get an idea of microplastics abundance in the environment. So that's great if we can increase the number of samples so that we can really get a better picture of what we find in the environment. But that creates a new problem, kind of similar to what Artur mentioned before. Like when you make a solution, you usually make a new problem. And our new problem now is that, okay, we have all of these samples, but we need to find a way to analyze them. Because up until today, microplastics analysis is one of the steps in the process that is really the slowest and causing quite a bottleneck for enabling us to really carry out extensive monitoring of microplastics in lots of different environments, not just the ocean, but also things like drinking water or in soils or sediments. So just to give you a quick overview, microplastics analysis usually ends up with some sort of filter. So you usually take what you find and you filter it, and then you look at the particles that you have there, and you have to kind of decide which particles are plastic or not. And we usually do this using spectroscopy. So either FTIR or Raman spectroscopy are really common methods, but they really depend on a one particle at a time analysis. So you have a look and you think, okay, this particle looks like a plastic, I'll check that one, and then that one, and then that one. Whoops, I skipped ahead there. So here it takes a lot of time because you really have to go through the particles one at a time, and it's very intensive and very slow. So in order to kind of speed this up, there is some technology that's kind of up and coming, which is really promising for allowing us to increase the throughput of these analyses, and that's called a hyperspectral camera. And a hyperspectral camera is essentially like a regular camera where you have 3 channels that are RGB, red, green, and blue, but now you've got like 100 channels, let's say, for each wavelength. And we can operate in lots of different parts of the electromagnetic spectrum. And what's interesting for chemists like myself is the near infrared region, because in this region, we get a lot of information about different chemical bonds, especially organic compounds, and we can actually use the spectra from this region to identify polymers or plastics. So what that looks like is that you get this kind of fingerprint of what a plastic or a polymer looks like, but you get one of these spectra for every pixel in an image. So if you think of like a regular picture, every single pixel in that picture will have a spectrum associated with it. And that allows you to identify where the plastics are in the image. So instead of going particle by particle, we can just take that filter and we can use this hyperspectral camera that you see in green here, and it kind of like really quickly scans over the whole surface of the filter, giving us this picture with all this spectral information. And then we can use chemometric modeling to identify which of those spectra belong to plastics, and we can kind of highlight those ones. And then we can see how many and what type of plastic they are. So this really allows us to increase the amount of samples that we analyze in a very short amount of time, which is super great when we have replicates because we've been able to sample more. So hopefully we will scale up sampling using Pamela, our USV solution, but now we can also scale up the analysis using hyperspectral imaging. So we really hope that this can kind of contribute to the entire microplastics scientific community and allow us to really scale up sampling so that we get more representative pictures of what our environment looks like with respect to plastics pollution. And that will help us inform things like policy to either clean up or protect specific areas. We can identify regions that are really highly exposed and prioritize them. So this is a super important tool for allowing us to get a clearer picture of what's really going on in the environment, because right now it's super patchy and we really just don't have enough data to be saying anything concrete. So thanks so much for attending. Really appreciate your time. If you're interested in the portable catamaran drones, or if you know someone who might be able to use this tool, we really encourage you to reach out and get in touch. Our email addresses are here, so go ahead and screenshot that if you like. And yeah, there's the paper that Artur mentioned in the bottom. So please have a look at that if you're also interested in more of the technical details on that side. So thanks so much.
Thank you so much. It's incredibly interesting to hear the work that you're doing. I don't see any questions in the Q&A box or in the chat yet, but I encourage all of our attendees to send through any queries or questions that you might have for the speakers today. I'm going to start, Artur, with you because you went first. You did preempt quite a few of my questions in terms of the different conditions that the drones have been tried in. From my understanding, is the majority of the sort of tests being conducted in sort of Norwegian seas? Is it relatively sheltered with the fjords and that kind of thing? Could you expand a little bit more on the kinds of conditions that you sort of that it's maybe been designed for? Obviously, there will be a lot of variability depending sort of how far out it's going as well, I assume.
Yeah. So yeah, that's true. So for the last few months, we tried to expand, our knowledge about the vehicle performance. So our test started in Norway. The very first tests were in a quite sheltered area, where on the student course, where we just see, okay, the vehicle works at all. But then we moved on. The tests performed by Andrea and Caprim at Runde were in quite exposed waters, actually without any protection, where we experienced like Beaufort force scale waves. But then again, there is a certain issue in Norway. You will never test it in the high temperatures. So then we collaborated with our colleagues from working with the plankton net as well, and they were kind enough to take the robot with them to Ghana and Tanzania, where they tested robots in different regions on very high temperatures, like 30 over 30 degrees, to see if the vehicle performs very well. And it gave us some indication about, okay, what to improve when it comes to transportability, which part need to be more endure more. We're also experiencing a different type of items we can see in the water. So just an example, in Norway, there's not much contamination in the open waters, but then you can have a kelp entering the thruster. So we need to provide a kelp guard. At the same time, the same kelp guards were useful in other regions where there was like a plastic bags floating in the area. There was samples. In one region, we are getting jellyfishes in the net. In the other, like microplastic particles. So also we, when experiencing different areas, we experiencing different currents, like on rivers, or there are some situations, some places where that we didn't expect there will be like a pole sticking out of the water. It's hard to navigate, in the autonomous mode around them without like obstacle avoidance. So with every new location, with every new test, we learn more and we see, okay, what to focus on our future improvements on. Also for another scenarios, we haven't tested yet, but we've got some indication, may be interested. Like in the mountains in Pyrenees, to leave the robot for a whole day, to make it sample during the night when the water mixes in a different way, so the researchers don't have to be there, just come back in the morning to pick up the sample. So we try to expand our network, we try to expand the use cases and learn more and figure out, okay, we have this new tool, people need to learn this tool, and also new scenarios will come because the new features are enabled. So yeah.
Okay, very interesting. And in terms of, are there any specific sort of plans or accessories for the particular catamarans to account for catching macroplastics and any biological material and that as well?
So since we build this vehicles from scratch, of course, using the commercially available components, we have quite big control of what we do. So, for instance, we get the request to navigate at higher current, so we can increase the number of thrusters. Others would like to, for example, get additional sensors. So we are also planning on expanding on water quality sensors. So you collect not only the sample, but also measure the environment. We did the first trials of a vertical winch, where we take a vertical profile using a small net or using a CTD, for example. So when it comes to the size of the net, so far we try to focus on portability, because we see this is something unique for our design, and that people see the big benefit, because they are not worried to deploy it from a side of the boat. They will not fall off. We can carry it from the trunk of our car, or carry it in the check-in luggage. So we try to focus on the portability, but yeah, we are exploring the add-ons. We are exploring the features that will that will be most useful for the future users.
I see. It's very interesting. Andrea, I have a question for you for the hyperspectral imaging that you spoke of. So it's very interesting. I wasn't aware that you could use sort of near infrared to detect polymers. Is that at a relatively small scale? Because obviously I think the use of near infrared and infrared to detect vegetation on a wider scale is somewhat common and more established. But detecting plastics, can you tell us a little bit more about that? Has that been around for a while? Is it as commonly used? And at what scale does it work? Because obviously, if you're looking at the filter that the drones have collected, that's a very different sort of scale.
Yeah, absolutely. It's a great question. So as you mentioned, near infrared is used quite often for vegetation. It's also used a lot of times in remote sensing applications, like on satellites, for example. And another kind of like really relevant application is actually in recycling plants. So in recycling plants, near infrared spectroscopy has been used for quite some time to sort different plastics into different polymer types, so that you can get a more pure waste stream. So this is like a pretty clear indication that near infrared is really capable of identifying and sorting different polymers, and it's something that's been used in kind of a different application, different industry, but it's only just now starting to kind of show up in microplastics analysis and looking at specifically more like the macro size, to be frank. So kind of in the, like, we typically define microplastics as below 5 millimeters. As of right now, most of the near infrared instruments, they're operating on a scale that is usually kind of like around the millimeter size and upwards. But that has a lot to do with just the way the instrument is designed, right? It's typically, as I mentioned before, we're co-opting a lot of existing technologies to analyze microplastics. And this is kind of another example where a lot of these near infrared hyperspectral cameras, they're actually made to analyze much larger items, right? So either they're used for remote sensing or for more of kind of this, if you think about like a garbage or like a recycling plant scale, where you have larger items like water bottles that you're going to image and sort. So it's kind of like a limitation in terms of the instrumentation that's available right now to look at smaller particles. But in terms of the particles that you're actually collecting in a manta-trawl, usually the cutoff is about 300 micrometers. And most people are going and sorting those particles by hand. And usually the ones that you can kind of see and actually pick out and analyze are going to be around 500 micrometers. And there's actually been quite a few publications rather recently that show that hyperspectral imagers can analyze particles down to 500 micrometers. So it's a super like kind of new application. There's not a lot of work done on it quite yet, but I'm personally working on it as a part of my PhD, and I think it's a super promising technology. So I mean, it's got its roots elsewhere, but people are being creative, researchers are being really creative and finding new opportunities for good analysis.
Thank you so much. It's very interesting. As you were sort of explaining it and everything, I realized I understand that the sort of recycling sector in Norway and in quite a bit of Europe is sort of quite automated, and as you mentioned, the use of the sensors there makes a lot of sense. From the African context, it's, to my knowledge, it's often a bit more sort of more intensive manpower. To my knowledge. I do see that we have another question that's come through here saying very innovative work. It's interesting to see how you've worked together to find a solution and the degree of learning and flexibility that's been evident in your research. So it's very interesting. I see we are approaching the 12 o'clock mark. If anyone does have any questions at a later stage, you are welcome to send those through. But we do have time for one or two more. So if anyone wants to send those through now, you are still welcome to. I was wondering, for either of you, could you comment a little bit on the on maybe sort of some of the specifics for the drone? So the mesh size that you're using. I know, Andrea, you just mentioned that the typical manta ray mesh size would be about 300 micrometers. Is that the sort of current one that you're using? And is there any sort of restrictions in terms of speed that the catamarans can travel?
Yep, I could take this one. So as I mentioned, yeah, we're operating with 333 micrometers. It's kind of standard size for manta trawls. We have used other mesh sizes. So Artur mentioned briefly that we also were looking at collecting salmon lice larvae for monitoring salmon lice, which is a big problem in Norway. Obviously, we have a lot of aquaculture here, and finding and monitoring salmon lice is quite a hot topic. So I have a colleague here at the biology department who's looking at ways to monitor salmon lice. And he used this drone to collect trawls looking for salmon lice, which are quite a bit smaller. So we were using a mesh that was 180 micrometers for that project. And we didn't have any problems with operation. So that was really good to know. Obviously, the smaller the mesh size, the more drag you have, and then that will affect how fast you can go. We kind of like operate on a base speed of about 1 meter per second for kind of a regular manta trawl, but the speed can also be adjusted. So we can go faster, we can go slower, depending on the application. And we can also hook up a second battery and increase the power if that's something that's required. And that can go towards both increasing the power, but also increasing the running time. So those are things that we've also done to kind of custom make or tailor our solution to different applications.
Okay, wonderful. I see another comment has come through saying thank you for your important and for the important work. Wonderful to see the advancements using drones and cameras to ID microplastics there. So it's very encouraging. Before we close, do each of you maybe want to sort of share one or two maybe sort of challenges that you've overcome in this whole process? I'm sure there have been multiple, but perhaps one or two sort of key moments that you want to share before we close the session.
Yeah, sure. I mean, from my side, I've mostly been kind of working on the field testing, and Artur has been kind of the backup support. So I think one of like our main field campaigns on the exposed coast of Norway, I was working in pretty harsh weather conditions, and Artur was in Poland providing remote support. So I was kind of on the phone the whole time and had like one hand on the phone, one hand on the drone, and he was kind of giving me instructions. And if something went wrong, then I would suddenly have to start, screwing apart the drone and fixing things. And I was kind of just like doing what he told me to do and hoping that it worked out. But I think I learned a lot in that process, and I'm definitely like, really enjoying the multidisciplinary work here and getting to learn a little bit more about his field. So I really appreciate it, but definitely moments where it's, pouring rain, there's waves crashing, something's broken, and you're trying to fix kind of classic field work story, I guess.
A very hands-on learning experience, it sounds
very
like.
Much so. Very much so.
Artur?
Yeah, I think I can relate to the very same experiments because as Andrea said, I was sitting comfortable at my apartment, but then, I see the telemetry of the robot when they fight on the waves, seeing it going up and down and then controlling manually without seeing the vehicle physically, which was like, 1,000 kilometers away, controlling with my joystick, looking only on the map where it's going. It was also quite an exciting experiment. Back then, we were also learning about how important the kelp guards are. So, for example, releasing the drone remotely, controlling it from 1,000 kilometer away without seeing it to get out of the kelp field. Those are the learning experiences that you will not get in the office work at university usually. So
I see. Very, very interesting and unique experiences, I'm sure. Thank you so much, everyone, for joining us today. It's great to have you, and we have one final session taking place next week, Wednesday, on the 29th, at the same time. We hope to see you all there, and thank you so much to our speakers today. Thank you, Andrea and Artur. It's been very interesting to hear about the sort of developments and the process that you've had to go through, and I'm sure, as you've mentioned, there have been many challenges along the way, but it's very encouraging to see the progress that's being made. So thank you so much. I think we'll close off the session here for today, and hope to see you next time. Thank you so much, everyone. Have a wonderful rest of your Wednesday. Bye-bye.